Let us now look at the forces on the right-hand side of the equation we just developed for momentum. First, we'll look at pressure, which is the first one traditionally looked at by mathematicians and engineers like D'Alembert and Euler. So first of all, you might say, what is pressure? And pressure is the internal stress of the fluid. It's a scalar quantity, and it does not depend on a particular direction, especially when within a fluid. Remember, it occurs everywhere in a fluid, not just at the surfaces. In a fluid parcel, we might evaluate it at the surfaces of the fluid parcel and not internally, but fluid parcels are infinitesimal anyway. We will define a positive particular pressure. We'll give a compression force, and we'll think of it, that compression force is pointing inward towards the body of the fluid parcel. A particular internal pressure, or we'll say a static pressure in this case, is defined in a similar way. We'll say once again that the fluid parcel occupies a particular volume, delta V. The force exerted on the fluid parcel will be induced by the pressure, and it must be a particular force. And remember, we're writing these as capital after they're integrated. And subscript P for pressure will be integral of a volume of P times the vector V of delta sigma. We'll take this particular definition of the force from the pressure over the surface with the volume, and using Ostrogorodski's formula, and write it into the following particular equation. F sub P will be a negative, by definition, of the volume of nabla P dx of the volume. Then we'll be able to write F as the negative nabla P by taking the negative inside. This definition, you can imagine, came from a similar one that we used when deriving the Navier-Stokes equation in the previous video. So now we can put negative delta P on the right-hand side of the Navier-Stokes equations as the first particular component of forces in Isaac Newton's law.